Alright, welcome to the first of a series of grounding videos. And this video is going to be focusing on the 76 Marshall and some of the grounding mistakes that Marshall made over the years. And they made variations on their mistakes with different models. This is a 76 Mark II Super Lead. And while you can tell that the board has been changed out because previous tech had butchered the original PCB and we went with this turret board that I did. Everything else in the amp is more or less the same, but I'm not doing the stock grounding circuit, the ground scheme. So what's the best way to approach this? They say that if you can't explain something, you don't know it, and that's true. But at the same time, it's like some things are like telling someone how to tie shoelaces. It's a very easy thing to show because we deal in some information in visual ways. So I can show you how to tie your shoelaces, but it's very difficult to do a step-by-step process that can be communicated verbally or written. Similarly, this is a very deep subject, and I don't want to focus on French intransitive verbs if you're still working on quelle So, if you have questions after seeing this first video, put them in the comments. It's not going to be a monologue on my part. This is going to be a bit of a conversation as we go through grounding in different amps. And before I do anything else, I want to send you to another website. A guy named Merlin Blenko, also known as the Valve Wizard. He's a very nice guy. He's a very clever tech, and he has got a very good chapter on grounding. It is kind of the most crucial bits you need to understand, and some of it will make the rest of this video more clear, and some of it will be confusing at first, and maybe in this video and subsequent videos I can explain what he's talking about. So the link is in the description below. Go read that chapter and then come back. I'll wait. Read faster. Okay, good. Everyone's done, and now we're ready to look at this. Now, what Merlin described, what Merlin described was kind of the ideal ground scheme that would be done in a new amp, a completely new design, and it's hard to make an existing amp like a Marshall conform precisely to his ideals. But we can try, and we can incorporate some of the most important bits. So let me show you this first. This is a very simplified drawing of the schematic of a Marshall Super Lead or Lead. So this is the first preamp stage, VP1, which has the two inputs, and VP2, which is the second and third, well, the second gain stage, then the cathode follower, which is pretty much unity gain. And then it's going to show the phase inverter. Now, notice the big spaces there, those weird symbols I have. Those are capacitors. Those are coupling capacitors, or you can think of them as decoupling capacitors. And they are what separate one stage from the next in conjunction with the interstage dropping resistors and the filter caps. There's not going to be any math on this test. To make it more clear what I mean, here is the standard symbol on a schematic for a basic capacitor. And here is what I've done on this, where I've expanded that gap to make it more clear how they work. DC reaches the input side of that capacitor and does not pass through to the output of that capacitor. It blocks DC from one stage from going to the next. Now, it blocks DC, but it quite happily passes AC through that same capacitor. And the audio signal that we're generating is AC, and it kind of hitchhikes along with the DC. The DC at a tube goes from a low level to a high level. It takes the AC signal with it and amplifies that AC signal, and then after that stage, it goes to a capacitor which blocks all the DC and leaves just the hitchhiker, the AC, the audio that we want. Now that is a simplification, and before anyone goes into the well actuallys, Let's just agree that that is a general principle of how this works. And we're not going to get into high-pass filters. We're not going to get into impedances of stages or load lines. This is not going to go that deep. This is going to be an overview and showing the problems that ground schemes itself themselves can cause. Now, if you look at this drawing, you'll notice that I have the first two triodes with their inputs, and everything within that triode stage is tied to the cathode of that triode, and then both of those triodes are sharing the same filter cap. And I call this filter node VP1 for V tells me it's the voltage node, P for preamp, 1 because there are two preamp stages in the lead, super lead, or 5F, 6A basement for that matter. And so if the positive of the node is called VP1, I call the negative of the node VP1 0. And you'll notice that everything in a triode, on the front side of a triode, is tied to the cathode of that triode. And then the cathodes of both those triodes go to the negative of the filter cap for that stage, VP1 0. And what you want is all the stuff within a triode stage to go to the cathode of that stage. And then however many triode gain stages are tied to particular filter cap, then the cathodes of those stages then join the negative of the filter cap. And we're not going to get to where that negative of the filter cap goes at this point in the video. That's coming. Then you see that the outputs of those two plates, of those two triodes, that has high voltage DC, go to coupling caps. And that's where the DC stays with VP1, and the AC passes over to the VP2 stages. So VP2 is the next B plus node. And you have the volume pots and mixers and stuff going to the first triode in that stage. And all of that stuff, the volume wipers, the volume grounds are going to the cathode of that next triode stage. And then there's another triode stage right after that, which is the cathode follower. And its cathode doesn't have anything else tied to it in the simpler form of this circuit. And those two cathodes for the two triodes in this stage then go to the VP2 0 node negative. So you have a node positive, which supplies the plates of both those triodes, and the node negative, which is not going to chassis or what we would call ground at this point in the discussion. And then from the cathode of that second triode, then it goes to 3 coupling caps, and you can see where they split. And all the DC from VP2 is blocked at that point, but the signal passes through. Then we go to the next, which has the other side of those 3 coupling caps, and that's where it goes to the tone stack. You've got treble, bass, and middle, and then you have the phase inverter, and it has its negative, its actual cathode is through the presence pot, and you can see that the mids of the tone stack are going to that same cathode position. So everything from the tones in the tone stack is grounded not to the preceding stage, VP2, but to VD, which is the driver stage or phase inverter stage. And that again has a positive and a negative. So we have VD, we have VD0 with its own filter cap. I've not shown the outputs to the tubes, to the output tubes and the screen node and the anode node, because this is getting the point across that every triode and everything connected ahead of the grid of that triode should have its ground reference to the cathode of that triode. However many triode stages there are on a particular voltage node, B plus node, should then have their cathodes referred to the negative of the capacitor, the filter cap, for that node. So everything in VP1 has its cathode tied to the negative VP1 0, VP2, VP2 0, VD, all the cathodes go to VD 0. Now notice on this drawing I do have negative feedback shown. That's where the negative feedback joins this circuit in the phase inverter right before its presence control, which is how the whole thing goes to ground on its cathode, which then goes to VD0. And that complicates things, but we'll get to that. Right now, let's move on to viewing this as a block diagram. All right, this block diagram is a simpler version of what we just saw, and this is done to the ideal ground scheme shown in Merlin's chapter, where we have the two triodes in VP1 are shown as triangles, showing all the stuff coming down to its cathode, and then the cathode goes to VP1 0, which then, then you have VP2, all the two stages in VP2, and their cathodes are going to VP2 0. Then you have VD, and its cathode goes to VD0. And VS, which is the screen supply, going to VS0. And VA, which is the anode node. Anode is the British term instead of plate. And I wrote anode instead of plate here, so we don't have a confusion between VP for preamp and VA for anode. And that has its own VA0. And if you read the Merlin chapter, you'll see why it's very important that nothing else goes to VA0 from the rest of the amp. And that has it in the ideal path that goes to all that in sequence from VA0 to VS0 to VD0 to VP20 to VP10 and then to chassis right at the input. And all of the reasons for that are explained in his chapter. So this is an ideal thing. And it's very important that you note the flow of current. It's not just the voltages going on the top side, the positive side. The current is also going to flow on the negative. And so you want to have the sequence correct from the VA through VS through VD through VP to the input. So that's the ideal thing. But that's not what most amps do, most vintage amps, because it is a difficult thing to actualize. You really, if you're going to do this, you need a very large trace or a very large bus wire to handle that current. Now, on a very high quality PCB, this can be realized with a thick copper trace for all this. And you can steer that ground path precisely and observe all the rules and have a great sounding amp. And there are companies that do that. John Sear's amps do that on his PCB boards. It's crucial stuff. A lot of PCB amps don't do that because they're built or designed poorly. They're not really following the rules, and as a result, you get high noise floors and strange buzzes and stuff. But anyway, if you're not going to do that with a PCB, the next way to do that is with a very thick bus wire, like 14 gauge, that everything is tied to. Now, it's crucial that if you do that, the bus wire is only tied to chassis at one end, the input end. And I don't like adding that to old amps like this because you have a big wire suspended pretty much in air for most of its length, and you have some support from whatever components and wires are connected to it, but it's adding a lot of mass that vibrates. And the dirty secret is you don't have to do it this ideal way to get really good results with most amplifiers. Now, if we're talking real high gain stuff, diesel, VHT, Uberschall stuff, then you absolutely have to follow this kind of design to the letter. You cannot cheat. But with a classic Fender design or a Tweed Fender or a Marshall through about 1983, you can kind of cheat. Let me show you the ways that Fender cheated, which worked well, one way that Fender cheated that didn't work so well, and the way Marshall cheats on most of the Plexi and 70s amps that has problems. So here we have what Fender did, both in the Tweeds up through late 57 and from 61 to about 83. The brown, blonde black and silver panel eras. So here they don't have the triode cathodes connected to the negatives of their stages. You know, VP1, VP2, VD, VS, 0, et cetera, But what they do in the amps, which works very well, is that they will have all the grounds and the triodes of their stages connected to chassis in the series that it needs to be. So the input jack, everything flows more or less towards the input jack. So the noisy stuff is farthest, then the screens, you know, the VA is farthest, then the VS is closer, the VD is closer, the VP2, VP1, all that stuff goes towards the input jack. And so that's what they're doing with all their cathodes and pot and volume pot negatives and the tone stack connections. And that works really well. What they're doing with their filter cap negatives, the VP1 0, the VS 0, the VD 0, the VA 0, they are tying VS, VD, and the VPs together within the doghouse and or on the board, if you're talking pre-58. And then those wires connect to the chassis near the input as well. And the VA, the noisiest ground of the amp, goes to chassis at the other end of the amp by the power transformer. And that works really well. It maintains the general flow of current in the ground scheme in the same direction that you, everything from noisiest to quietest is going where you want. And that is something which can work very well in most amps if you don't need to observe 100% perfection. And that's an awful lot of amps. You know, you're talking a Marshall Super Lead, you're talking an AC30, you're talking a twin reverb. You can get away with it as long as you do it intelligently. Now, from 58 to 60 on the Bassman and Tweed Twin, Fender had a problem. All their amps up to this point had been done in a fairly small chassis. That was, you know, think of a Tweed Fender, the combos, they're all combos, and all the controls are at the top back, and there's just a little rectangular chassis that hangs down, and it's not very tall, and it's not very wide, and it doesn't have a lot of space. When they came up with the higher power Bassman and Twin in 58, they could not fit the filter caps inside the chassis the way they had on previous amps. So they went to a doghouse cover on the back of the chassis, which is I'll show you a picture. It's just a metal tray. And on the Bassmans and Twins from 58 to 60, they just jammed all the filter caps inside that, with wires coming in to the positives of all the filter caps, but all the filter cap negatives were just connected, hard soldered to the shell of that doghouse cover, and then that would be connected to ground, to chassis, just by the screws holding that doghouse cover in place. And so you're relying on metal-to-metal contact, where that metal-to-metal is not very tight, air gets in, oxygen gets in, you can have degradations. It's not a very good physical support for those capacitors. And Fender didn't do that for very long, 2 years. And they switched over to what we have now in most of or what we associate with a Fender, where inside the doghouse panel was a little fiberboard which mounted all the filter caps securely, and had wired grounds to chassis, which was much superior. And again, they were able to observe the VA, which is the reservoir cap, going to chassis along with the HT center tap near the power transformer. But all the other nodes, VS, VD, VP, VP2, but more than one VP if present, like in a late 60s Bassman, would have their grounds together, and that wire would connect near the input jacks. So again, they're maintaining a better signal flow. It's just 58 through 60 that the signal flow was not great as far as the ground, and it's not very reliable, and frankly, it's not very safe. But speaking of 58 to 60 Fenders, when Marshall came out with the JTM 45, they were copying the 58 5F6A basement, including the fact that they copied the values on the schematic that Fender had out, which are not actually the values that Fender did in most of the production amps. So there are some variations right there between the JTM45 and the actual basement that was sold and that people used, in addition to Marshall using different transformers and different output tubes, because 6L6s were very expensive in England at the time. So that's how the JTM45 began to branch off and be different from the basement. Right from the start, they copied the actual schematic rather than the amp as it was built. But Jim Marshall and the guys looked at the doghouse thing that Fender was doing with all the caps crammed into this little metal box and kind of haphazardly done and not great, and said, we're not going to do that. And they decided that they would incorporate multi-section can capacitors, which would be chassis mounted, and they look like this. And that allowed them to have an amp built without the doghouse, and an amp where as long as they could have the chassis punched, it was easy. There's a standard diameter. They could change the value of the caps in there, no problem. But the problem with the Marshall filter caps, multi-section, is that if you have more than one node shared in a multi-section filter cap, they by necessity share a ground. So you could not steer the ground as well, which would not be as big a problem if they had kept the layout of the multi-section can capacitors in the amp still flowing from loudest, noisiest to quietest from the back of the amp to the input jack. They did not do that. Here's what they did on this particular plexi, and there are variations on that. They've got VD0, the phase inverter filter cap, farthest away from the input jack. And then the next closest is VA0, which is the noisiest one, and then VS0, the screen, which is a little less noisy. And then by the inputs, you have VP1 and VP2. And the problem there is that the ground can flow from VD0 in any direction at once, and it has to pass all the noise that VA0 injects in there. And I'm oversimplifying a little bit, but it's really not ideal as far as the ground path to have VD0 so far at the other end of things. And then they did another thing. Remember when I said that if you have a bus wire, it should only be connected to chassis at one point? Well, unlike the Fenders that you see in the previous picture, where all the cathodes of the various stages connect directly to chassis in sequence, they have all the cathodes here connected to a bus wire run on the back of the pots. So while you have the cathodes more or less in sequence, they have multiple paths to ground because they have the path to ground through the nearest pot and all the other pots. And there's a whole bunch of eddy currents and ground loops set up there because that bus wire is connected all along the back of all the pots, and there are multiple connections to chassis. And people view ground as ground, and that's not the case. You have to steer these things. Now, in Marshall's defense, they were coming from a different tradition of radio design, basically, where in England at the time there were a couple of prevailing thoughts. Number one was the shortest ground path possible was always preferable. And so with multi-section can capacitors, you do get a very short path to ground. It's half an inch or less usually between the negative of the multi-section can cap and the ground lug mounted right there next to it. So they observed that principle. One of the other principles at the time was that amps should have no screen grid resistors on output tubes, or if they must have as little as possible. And that's why you can see some Marshalls that came out, early ones, without screen grid resistors and without grid stoppers as well. And Vox did the 100 ohm screen grid resistor, drag kicking and screaming to it. So these were artifacts of hi-fi design theory in England at the time. And so they were doing what they thought was good, but is problematic. And short ground paths are a good thing, but not at the expense of the overall ground scheme. So what to do about this? So here's what we're going to do to improve the ground scheme in this Marshall without doing huge heroics. Number one, we're going to accept the fact that we have multi-section can capacitors. So over at the input end, we have VP1 and VP2, VP1 and VP1, the two different stages of the first triode, and their cathodes are going to go to the shared ground of VP10 and VP20 in the multi-section can capacitor. The input ground will go to that same point, and the stuff in VP2, the next gain stage and the cathode follower, those cathodes will also go to that same point. So that includes the input grounds, the cathodes for those four triode stages, and the volume pot ground connections. And so all that's tied there at the input. And it's all to the same point that that multi-section can capacitor is connected to. And then we are going to tie the VD, the phase inverter, and VS, the screen supply, together. Their cathodes are going to join VD0 and then go to chassis. And VS0, the screen filter cap, is going to have a longer wire going from that multi-section can capacitor to the same point where the phase inverter ground is connected to chassis. And this is for two reasons. Number one, that longer ground wire on the screen cap is not that long considering the current there, and it allows us to correct the signal flow through the chassis for the ground flow through the chassis. Second of all, and this is very important, because the VD, this phase inverter, and the VS, the screen supply, are all within the same negative feedback loop, they need to have the same ground reference. And if you separate those too much, you can introduce essentially a big ground eddy current there. So it's good to have those tied together. And those are going to chassis about midway through the amp. So we've got the input stuff and the second stage stuff, VP1 and VP2, all going to chassis right by the input jacks. We've got the phase inverter and screen stuff going to chassis right about in the middle of the amp. And the VA, which is the noisiest stuff, along with the bias, which I'm not referencing here, is going to chassis over by the power transformer, which is farther from the input. And so within the chassis, we will have essentially a giant bus wire, and the signal will flow where it ought. And this is kind of applying the good Fender ground scheme to this Marshall. And there's a guy named Larry, I can't remember his last name, I will find it and put it below. He's a very good tech in Germany, I believe, and he first popularized this, and it's known as the Larry ground scheme. And I think I stumbled upon most of this independently and then saw what he did and I'm onto something. And I looked at what he did, and we agree about almost everything except that he likes to connect the heater supply right at the input as well, and I like to connect the heaters to the screen node. And I think an amp could starve on the difference that they make, but I don't like running long wires when I don't have to. Now, there's some things in this Marshall that are not addressed in these pieces of paper. For instance, you can see that the output tube cathodes are going to chassis right by the tube sockets the way they are in other Marshalls. And I've got the ground wire from the output jacks going to one of those output cathode chassis connections. In theory, all that would go to the node, the ground point on the amp that I'm using for the screen and phase inverter points. And I've done that in the past, and it doesn't make a huge amount of difference, honestly. There's not a lot of current from the cathodes of the tubes. You can get away with just doing it at the sockets in this case, and there's almost no current in the wire from the output tube, output transformer negative to the chassis. There is current from the output transformer negative to the negative of a speaker, but that wire from that negative to chassis is just kind of a reference. And so I don't want to do any work which is unnecessary in these amps, even though theoretically it is better. And if I were building an amp from scratch, particularly with a PCB, I would implement that. But by moving the wire here from this phase inverter filter cap, the ground wire, to where it should be in the correct flow of the amp, that makes a good bit of difference, and I've done it both ways. Now you will also notice that I am not using the can cap mounting hardware for grounds. I have found that you get much better grounds if you have something which has no strain on it ever, and it has its own discrete connection to chassis. Whereas the transformer mounting stuff, it's a bunch of different kinds of metals. There's some mass on that. There's just a little bit of stress on that. So I have the original hardware holding the can caps in place, and that's all it's doing. It's just holding those can caps in place. And I've added new grounding lugs at discrete points in the chassis using stainless steel stuff. So I have steel to steel contact, which is just takes dissimilar metals out of the equation. And it's very rugged and won't go anywhere. Now you can see here I've got this screen and phase inverter chassis point, which does have the presence ground there, and the mids ground is going there, and the wire, there's a wire from the VD0 and VS0. So we've got the screen and phase inverter node filter cap negatives going to that eyelet. Not that eyelet, sorry, that ground lug. So we have all that tied at this point in the chassis. And then I've got another ground lug at the input of the amp, which I have not wired up yet, which will have the input grounds, the grounds from the volumes, the cathodes of those stages, the first two, well, I guess 4 triodes, the first 2 gain stages, if you think of it that way, and the filter caps for those nodes are all going to join right by the input. So this will make the amp conform much more closely to Merlin's ideal design. It will be, in effect, making it the ground scheme much more like a Fender, which is usually a very quiet amp. And I've done this on Marshalls, and it really dramatically lowers the noise floor. And you will notice that there is no bus wire across the back of the pots. It's not necessary, it does no good, and it causes a lot of noise and buzz and stuff that people think is just part of the sound of a Marshall. It doesn't have to be. You can get rid of all kinds of extraneous stuff, and then it just leaves you with the music. And that's the important thing, in my opinion. And the amp sounds better without all that other stuff. I'm not going to get too far into it, but all the buzzes that we hear in amps are always some multiplication, some multiple of the mains frequency. So in America, that's 60 hertz. So you're going to get 60, you're going to get 120, 240, 480, et cetera, et cetera. These are the frequencies that are going to be behind and mixed in with everything you play. And all those frequencies are kind of in between a B and a B flat. And it's just like having one string slightly out all the time. I mean, you can hear it, and not only does it make things sound a little bit sour, it can affect sustain, it can cause weird artifacts, plus no one likes the sound of bzzz. So we're going to get rid of that, and you'll hear that in a follow-up video when this is done. Now, before you ask, yes, these are alpha pots. Yes, alpha pots are inexpensive. I have done CTS. I have done Burns. I have done precision electronics. I have tried every brand of pot out there, I think. Alessandro's, which just rebranded Precision Electronics, et cetera. Old stuff from the 60s and 70s, new old stock stuff, Clarostats. And I have found the following. CTSs can be great, but at least in the last 5 years or so, they're audio taper pots. I hate the taper. They go from nothing to, wow, that's loud. There's just no gradual transition at the bottom of the range. And they have some which are much better, but that's often in a J taper, or the better value pot is only available in the values that we need with a knurled shaft as opposed to a set screw solid shaft. I have found that Burns have gone down in quality. I have found that PECs cost an awful lot, and the premise that they will never need cleaning because they're sealed is not true. They develop scratchiness, then it's really hard to open them up and clean them out because they've got a very rigid stainless steel shell, and it's enclosed, but it still gets noisy. And these alphas sound really good. The tapers aren't the same as the old ones you'd find in a 60s or 70s Marshall, but the tapers are very good, and they don't go from nothing to loud. They're easy to clean as needed. They sound quite good. I see no downside except a perceived level of snobbery. So I have done an awful lot of amps that people rave about the sounds of with these alpha pots. And I would love to use a very esoteric, expensive pot just to satisfy those who like to sniff corks. But as far as performance goes, as far as sound goes, these are really good in a Marshall. These are really good in a Fender. There are things in Fenders that I don't use these in because I want a J taper here and there. That's for another subject. But it's almost coincidental that these alpha 24mm 3/8" bushings are fairly inexpensive. So consider that just a gift from the universe, that a good sounding, reliable pot that does a great job, that's easy to clean, that is very musically responsive and intuitive, also happens to be one of the cheaper ones on the market. Who knew? Anyway, I'm going to wrap this up for right now because I've got a lot of editing to do and I've got a lot of other amps to work on. But I think this is a good start to a series of grounding videos. And like I said, put your questions in the comments. Try not to show off how smart you are for the rest of the class. There are a lot of smart people who watch these videos, and it's not a contest. And please don't do the what about things trying to one-up me, because I am trying to do this at a level of discussion that most guitarists can understand and then take with them and apply that to their understanding of other amplifiers. I'm not trying to show off my technical knowledge here. That's an entirely different vocabulary, and I can hang with anyone if we want to get into all that bullshit. This is not about whipping it out and measuring it. This is about communicating real-world stuff about circuits for real-world players. And it's not about how smart I am, and please don't make it be about how smart you are. It's about how good an amp can sound with some TLC.